Okay, great, thank you. So I'm really excited about this panel discussion and the conversation that we're going to have here. So let me just briefly introduce the folks on this panel. So on my left, we have Diyi Yang. She is an assistant professor of computer science here at Stanford University. To Diyi's left, we have Risa Wechsler, professor in physics, particle physics, astrophysics, the director of the Kavli Institute for Particle Astrophysics and Cosmology, as well as the director of Center for Decoding the Universe, which is one of the research centers here at Stanford Data Science. And next we have Madeleine Udell, who's an assistant professor of management science and engineering at Stanford University. And last but not least, we have Carla Pugh, who's a professor of surgery here at Stanford School of Medicine and the director of technology-enabled clinical improvement. So it's my great pleasure to have this wonderful lineup of panelists. So first, I'd love for you all to just explain a little bit about how your research intersects with data science, maybe some of the ways that you are using data science in your own research to kind of further discovery. So maybe we could start with Diyi.
Okay. So I work on natural language processing. So data to me is just natural language in English, natural language in Chinese, in low resource language, in different type of languages. And language is also everywhere. So you have social media posts. You have a lot of our health records in natural language, etc. So I can enumerate all possible data in my daily research. So the research I work on is to think about giving so much structured, unstructured data, multimodal, not only just text, but also audio, images. How could we make sense of those data? How could we build AI applications that could leverage those data for some kind of discovery? So recently, some of the projects we have been working on is to think about, can we build audio models that can really understand not only our text, but also our emotions, tones, accent, a lot of the social signals, human factors that we carry in models. So this requires we kind of think about, is the classic architecture of doing automatic speech recognition needed? Do we need to think about it from an end-to-end fashion to kind of understand them? So we have been building models, large audio models, and also different evaluations to think about those nuances in data. Because those nuances can really matter in high-stake scenarios, thinking about someone who is like looking for help in a very urgent fashion versus looking for help in a relative chill fashion. Tone or a lot of the signals may tell you a lot, and if you only look at the pure text, those signals are going to be lost. Not only this, later today I will also share our research on how we actually use this kind of data to better help people in picking up social skills. Many of us have situations like difficult conversations to navigate every day, or you want to learn a new skill in negotiation to better prepare for your career. But large language models have a lot of those data from internet. Maybe they can use those data to help you practice, to give you feedback, etc. So to me, I think data is the foundation of how we build AI models. We get to know a lot about data. And then the question is, who produced data? It's human. So that's why, like, in my own research, I try to not only just look at data, but also the providers, the producers of data, to think about how we bring in human factors into the development process.
That's great, thank you, that's so interesting. I'll also say that Diyi is our closing keynote speaker as well today, so if you want to really do a deep dive on some of Diyi's work, then definitely stay for that. Risa, would you mind going next?
Yeah, so my training is as a computational cosmologist, meaning that I use large computers to essentially model the entire universe, how structure forms from the earliest moments of the universe when we just have tiny fluctuations to build all of the structure and then all of the galaxies, the billions of galaxies, hundreds of billions of galaxies that are in our universe today. So that's what I do on the modeling side. for the last 20 years or so, I've also worked with very large teams to build telescopes to make the largest possible maps of our universe. And you said that data is human constructed. Some of my data is human constructed in collaboration with computers. But the most interesting data that I use is definitely not human constructed. It's constructed by the universe itself. And the data that the universe produces is extremely interesting and complex and also multimodal. We have images, we have time series data, we have spectra that tell us for individual objects their light as a function of wavelength. We want to put all of these things together for billions and billions of objects to extract the most possible physics that we can. And we're in a real renaissance of data in astronomy. We've actually been a data-rich field for decades, but it's about to accelerate. One of the projects we're most excited about, we built a 3.2 gigapixel camera just down the road at SLAC. Literally today, that camera is being installed on a new telescope in Chile. And very, very excited about this. So my colleagues are there trying to install this camera about the size of a car on a telescope about the size of this building. And that camera is going to deliver about 15 terabytes of data every night. It will survey half the sky, the entire southern sky that it can see from its mountaintop in Chile. And will not only take pictures, it will essentially take movies. Every part of the sky it will see on average every 3 days. And so we expect to really be able to discover new things that we've never seen before through anomalies in time series data, anomalies in the multi-wavelength data. So one of the big challenges that I'm personally very interested in, which I actually think has analogs in many, many fields, is that, as I told you, I try to make models of the whole universe, and then we observe the universe. We want to really use all of the data we can to constrain the models. But of course, the models are not perfect. If we understood how to model the whole universe, we'd probably be done. So we have this challenge where we have relatively computationally expensive models and very complex data, and we want to do real inference that uses all of the data. And that is not something we've solved. We solve parts of that problem at a time. If any of you want to help me solve the whole problem, I would love to talk to you about it. So I'll leave it there, and yeah.
Yeah, wonderful, thank you. And I'll also put another plug. I think that there is a Decoding the Universe event coming up. So
yes, June 5th and 6th, we're going to have a conference in this space.
Oh, perfect. Yeah, so again, if I find it hard to imagine that this wasn't interesting to everybody. So yeah, put that on your calendars too. Thank you. Madeleine?
So my research is in mathematical optimization. So the way that I touch data is much more abstract. I'm interested in data from all different domains, and I'm interested in understanding what kinds of mathematical structures are driving the data, are driving the data generation, and how can we use those structures in order to make more interpretable, accurate, and efficient decisions using all the data. So my research really centers on the question that you raised, which is how do we use all the data? How do we make sure that our decisions get better and better and better as we have more data and not worse and worse and worse and slower and slower and slower? So some of the structures that I look for are low-dimensional structures. I try to identify when the data that looks like you've collected so many different things about each sample, actually there's some kind of simpler structure, and if you had sort of the right coordinate system, you would be able to understand what's going on in a much simpler way. And so that drives a whole bunch of innovations. That drives, on the one hand, methods for interpretable machine learning, so that you can understand maybe a subset of the features that are important and how they influence the phenomenon that you're interested in. It also drives faster optimization methods. So no matter what you're trying to predict, perhaps we can use the structure of the data to allow you to predict that faster and more efficiently by first compressing the data down and then solving the problem. Now that sounds like you would solve an approximate problem, right? You wouldn't actually solve the real problem because that compression is always going to be noisy. And one of the things that I try to do in my research is to randomize that compression and repeat a randomized projection over and over again so that we can solve the exact original problem, right? Even though the compression is inexact and noisy. So I'm always using sort of going back and forth between different kinds of data sets in different domains, and then sort of understanding mathematical structures, right? So trying to make sure that I'm working on the ones that are the most important and the most sort of widely applicable.
So interesting, thank you. Yeah, Carla.
Yeah, no, thank you. This is all exciting. I want to speak with them about this.
Yeah.
So nice to meet everyone. Yes, I'm a professor of surgery in the medical school, and I also, my motivation for even coming in this space happened, it's hard to say, more than 25 years ago when I got a PhD in education here at Stanford and learned about sensor technology. And so applying that in healthcare, what I do is use sensors to quantify human performance. And broadly within healthcare, so anywhere from a basic physical examination to a complex operation, and I put sensor anywhere on anything on anyone to collect data. And it has been a 20-year journey that's been crazy, amazing, and very exciting, unfolding and discovering what it is that human beings really do. Many times we don't do what we don't say. You think about a professor who's world-renowned in making certain types of diagnoses using their hands. And when they give a lecture about what they do, probably about 60% of what's important for someone who's learning to understand what they do is completely missing because there's no words for it. The biggest, one of the, I won't say the biggest because there's another one that I can't talk about yet because I haven't published it, but the early one discovery that we made was that, and it seems obvious, all of our credentialing in healthcare is based on human observation. Well, humans actually can't see some of the parts that are most important to making a diagnosis. We can't visualize force. We can't track force. And it turns out the amount of palpation force, sounds kind of scary to say that, but how hard you press on something is directly related to whether you're going to make the diagnosis or not. So, so scale back. We're putting sensors on physicians, on training simulators that are already, used in medical school. And I think our biggest goal really is to develop an understanding of haptics broadly. Hand to a person, hand to an instrument. So I'm putting them on surgeons in the operating room. I understand everything that they do with their instruments. And beyond force, we've also started using EEG sensors. And now I'm able to synchronize motion, video, audio, EEG data in the operating room to understand surgeons and the team members. So I'm not only doing it for the surgeons, but the nurses, the scrub tech, the anesthesiologists, and wow. We are starting to understand things that we never understood before. And it's pretty exciting, and it's also daunting. And I'm thinking, great, I need your help with the language, I need your help with the math, and I need your help with, how do you really collect the data? Because you think about putting sensors on a surgeon in the operating room, it has to have the right profile. No, I cannot put a full 20 or 30 EEG cap on a surgeon in the operating room with a bunch of strings hanging on it. It just doesn't work. So form factor really, really matters. So in summary, for me, it's in two spaces. Unique situations in terms of how to capture the data, and then once I have it, how to analyze it. Getting it to be used broadly and become standards in medical education, that's a whole other part. And that is a great interest, which is exciting. So I'm working with the American Board of Medical Specialties, a bunch of medical schools and other people that are really interested, and they realize this is the future. And we as physicians have to drive it, or else someone else is going to capture the data on us and tell us what a good physician is, and that's going to be problematic. So there's a lot of motivations here with the data and moving things forward.
Yeah, Yeah, wow, thank you so much. And I guess on that point, obviously the point of today is to talk about data-driven discovery. Maybe Carla, I'm curious, with like this amazing data set that you are collecting, are you at the point that you've been able to make big discoveries yet, or have there been other discoveries in your field that wouldn't be possible without this type of data?
It's so, I love the question, and I have to say it's been so excited that I haven't focused on listing the discoveries, but one of them is exactly, there is a specific threshold of the amount of force that you need to apply in a breast exam. And we got a publication in New England Journal of Medicine telling people that for the very first time. And so it's been pretty exciting to have an exact number of the amount of palpation pressure that is needed in a breast exam. And physicians do it all the time. So we capture data we captured over 3,000 breast exam scenarios from physicians from all over the world in different specialties that do this exam. And we were able to look at those who got the correct answer across 4 clinical scenarios and those who only got 1 or 2 or 3. And there is actually something that the experts do. There is a human performance pathway. And we combined it not only with the center data, but the video data of what they do. So that's something that's not in the textbooks right now, and still have to go through. We're still stuck. I like your next question about hypothesis-driven research, because this is discovery. And so then now I have to take that and put it in a hypothesis to get more money.
Yeah. Yeah. Yeah, we'll get to that in a moment. But yeah, that's a beautiful example. Would someone else like to share some data-driven discoveries either that they've made in their group or that have been like made in their field that kind of like just wouldn't have been possible, say, 10 years ago?
Sure, I'm happy to go next. So one concrete project that my group has been working on recently is how to predict risk factors for heart failure using electronic health records. And there, the key feature that my group brings is that we can really use all of the data in the electronic health records. So rather than being driven by physicians' beliefs about which features are important for predicting the phenomenon, we can look at every single piece of data that's available in the electronic health record and winnow it down and figure out which ones are actually likely, really do seem to be predictive of whatever we're predicting. So in this particular application, we were looking at risk factors for heart failure. And we used data from Stanford Hospital to predict, and many features, and so we selected a set of like 15 features that were predictive of heart failure. And many of the features were things that we expected and that were sort of known in the literature. And one that was a little bit odd was whether or not you had had a pap smear. Whether or not you had had, not the result of that pap smear, but whether or not you had had it. And we said, that's really weird. Thank goodness we have an interpretable machine learning method so we can see that that's what's going on, right? We're not just doing this black box thing where all the features get mixed up, right? We can actually tell what is driving this prediction from all this data, and it's, but that's strange. We said, so probably it's wrong, probably it's spurious, you know? So, you know, probably you would want to sort of just delete that from your model, right? And thank goodness we can do that because we've got an interpretable model. And then we said, okay, but we're gonna do the right thing. We're gonna validate our model on a new data set. And so my student got access to the Veterans Affairs data set, which took quite a long time. He had to give like several blood samples and fingerprints and like, you know. So this took a while. And he tried out both of the models, the one with the whether or not you got a pap smear and the one without that piece of data, and it validated. In other words, whether or not you got a pap smear seems to be actually important. We don't understand why, but I would rate that as a discovery.
I have thoughts, but we can share later. Oh my goodness. Is that what you think? It really has to do with access to care, and it has to do with
Yes. I agree. That the most likely is that being on the ball with respect to sort of following the recommendations and getting the recommended care is an indicator of how assiduous you're going to be in taking care of yourself in the rest of your life, and that can probably prevent heart failure.
The amazing thing about the universe is every time we have like a new way of seeing it, we actually do discover new things. And so we're really lucky that way. And so we have lots of examples of data-driven discovery, especially of new kinds of objects. And very often those new kinds of objects really teach us new things. And that discovery can happen both in like synthesis of really large data sets, or it can happen, there's a really lovely example of a new kind of object that was actually discovered by citizen scientists just looking at images from large surveys. There's a kind of galaxy that was discovered by citizen scientists called green pea galaxies. These turn out to be very low mass but rapidly star-forming galaxies in the early universe. In the local universe that actually teach us something about the early universe, because they're kind of similar to the very first galaxies that actually reionized the universe, meaning their starlight actually cleared out the gas around them. So they're a very interesting kind of object that was actually just discovered by humans looking at images. In the next generation of data that is coming at us very, very soon, we know we're going to need new kinds of tools to make all of the kinds of discoveries that we want to make. And you know, some of those are going to be like, they're going to pop out right away as soon as we have a new window. And the ones that I'm actually most interested in are the ones that are harder, that actually, you know, try to put together all of the data and look for, you know, both outliers in multimodal data that are not there in the just one kind of data, and then also how do we actually learn new physics if we can put all of those data together in a model-driven way and really do you know, inference based on the full data sets.
Yeah, that's super cool. Yes. I don't study universe, but I'm very fascinated by it. When I think about the word discovery, I was really like asking myself, what does discovery mean? Because unlike natural science, in engineering, what we do is we build AI systems. And did we discover anything? I don't think there is a new object or things like that, since AI has been there for a long time. But to me, I think the discovery is a process. We have been building different components to understand the limitations and also new capabilities of AI systems. So from that perspective, it's a discovery. I want to share one recent study where we use AI to do discovery, since we want more discovery in the end. So this is a study where, think about like ChatGPT. Now it's so capable. They can talk to you, they can translate the language. Many years ago, not many years, like even 6 years ago, we didn't have a working system that can do translation from English to French. But today, it's just like amazing. So we were thinking about like, could AI actually help us with research as well? Like the research I'm doing every day. So what we did is that we built an AI system to generate novel research ideas by giving data. Data is all sorts of papers from arXiv, from PubMed, from the entire web. And then we let this AI to generate a research idea. We teach them what is good research idea, what would the idea look like. Think about when professors write funding proposals. We need to talk about here's the motivation, problem, method, experiment, and fallback plan, all sorts of things. And then we also have human. We recruit around 100 humans. They are PhD students from US. And then we let 2 groups do brainstorm on the same topic. So we give them 7 topics in natural language processing. And then the study lasted for 1 year. It's not a typical research we do because most of the time we work with static data sets. And then in the end, what we discover is that AI research ideas, when you get ideas produced by AI and ideas produced by human, and you make sure the format are exactly similar, like there's no like writing difference. And then you recruit a third party they are reviewers, just like conference reviewers. We let those reviewers read the ideas generated by AI and the human. We don't tell them which idea is which. And then in the end, we found that AI ideas are perceived to be more novel, equally feasible, overall quality higher by our human reviewers. This is very surprising and to some extent controversial and to some extent surprising and depressing to me, because I feel like being a professor, being a researcher is such an amazing job. And maybe to some extent, AI could also help or automate some parts of my job. So this is definitely very interesting discovery, and we are still trying to understand what does this really mean. If we let people to implement those ideas, do we get a similar or different breakthrough as what we have? And I think recently we have already seen a lot of breakthrough in this direction, where like deep research from different companies and also like co-scientists, where AI is being used as a tool to help researchers, professors with our daily research.
Yeah, great. So a point that I wanted to get to too, as some of you alluded to, is how does hypothesis-driven research interact with data-driven research? And those two things don't necessarily need to be independent from one another. You can do data-driven research with a hypothesis, but at least, Carla and Madeleine, it seems that you kind of discovered things that maybe you didn't hypothesize to be there. And I'm also curious if you have thoughts on how this interacts with our funding mechanisms, which are very hypothesis-driven, but this is maybe at odds with the amazing discoveries that you can make if you kind of go in with an open mind, let's say. So I'd love to hear all of your thoughts on that question.
Yeah, I'm crowdsourcing and changing my conversation, my thoughts about it based on what's been said here, and it's interesting. I've been a reviewer for grants. I mean, I sat on the study section at the NIH for 7 years, and you sit in that room, and when I think about what we're talking about here, there are specific study sections that relate to tech development and sort of discovery. So there needs to be more of that. That's the first part of the answer. There needs to be more that relate to discovery. And I think that will allow and enable a language and a pathway for those of us that are in this space of discovery. The other thing that, just in terms of I guess it's the National Institute, NIBIB, at National Institutes for Health, because they're technology development oriented, you can write a hypothesis. The main thing is that you don't want to, so it doesn't sound like a fishing expedition, you don't want to end your hypothesis is that we're going to discover something. Mm-hmm. You just take it the step further, that we are doing this to discover these types of things that will have this impact. So you have to go to the impact. And then your hypothesis is that you're going to have impact. So you skip the discovery, but you write it in a way that they know you are exploring, these metrics that will have an impact in this specific space. That's just sort of one pathway to enable the discovery component.
Yeah, thank you. Yeah, Madeleine, I'd love to hear your thoughts.
Sure,
as well.
sure. So in thinking about how I have traditionally conducted my research, I would say that I've often been hypothesis-driven in the mathematical transformations that I use to power my research. I think maybe a low-rank structure will allow me to, accelerate computation. Whereas I've been much more agnostic and data-driven in the sort of substantive discoveries that I might make, as the example in the heart failure data set that I mentioned. But recently, I've been getting really excited about data-driven discovery of mathematical transformations. And to be able to use, for example, modern AI tools, both generative models and reinforcement learning, to, what would it be like? What would it mean to sort of quantify the kinds of improvements in computations that, that applied mathematicians know how to produce, and put that in a loop and say, okay, well, try more. Please generate more ideas for more kinds of transformations that might accelerate computation and discovery. And now, just run that, keep running it until you find something new. What's interesting is that I think right now that's a little bit, it's still a little bit ahead of the time. Actually, I think that would be difficult to get funding for an idea like that right now, because people don't want to be automated away, right? It would be saying, reviewers of my grant, I am trying to automate you away, and people don't usually like that. But I'm very excited about that direction.
I'm curious in astrophysics how do things work in astrophysics? Is it kind of like, big data?
I would say I really straddle hypothesis and data-driven, and I am sort of in between physics and astronomy. Historically, physics has been much more hypothesis-driven, and astronomy has been much more data-driven. I mean, the earliest astronomical measurements of the motions of the stars and the planets, all of those discoveries were data-driven. For thousands of years, astronomy has really been a data-driven science. Physics has been much more starting with, the key ideas and then trying to measure specific things that you already know you're trying to measure. And my work is right in between and right at the interface, and sometimes more on one side and sometimes more on the other. I think they've bled together as all of astrophysics has been so data-rich. In my own work, I really do both of these kinds of things. In some cases, I'm really trying to measure a number, and I know what that number is, although sometimes the data surprises us. And what you really want as a physicist is to break your model and to discover some new physics, and that is always going to come directly from new data. I think but it is interesting. I think just this interplay that we do day to day, and the ways those things drive even subcultures within a field. There is this thing, it is actually quite hard to write a grant proposal that's just like, I'm going to have data in a new wavelength or a new time domain, and I'm going to discover something.
You can't do that.
That doesn't usually work, but that is actually where so much of the major discoveries have come in astronomy, is just opening up a new window. And it's one of the reasons we're so excited right now about the new windows that are opening. But at the same time, so many of those things, so many of the new discoveries we make are going to be when we put together things in different ways and then actually try to have some hypothesis that is where the data is really so sensitive in a new way that it has new potential to really break the models. And I think that's where we get really exciting things happening.
Thank you. Diyi?
I think those are all amazing. I don't use the word hypothesis very often. To me, I feel like when I think about data-driven research versus this hypothesis-driven research, is more about asking research questions to the data, because that forms lead to hypotheses that we know, or we probably have some prior about data, and then build upon those research questions. That's how we organize or arrange different type of patterns in data to inform a final kind of hypothesis. So to me, hypothesis is a process of searching for that, and then it always starts with many different type of research questions. But I definitely agree with a lot of especially when it comes to funding. Don't ask me this.
Also, I would chat with you guys just all day, but I want to open up the Q&A. If anyone has any questions for the panel, I'll be very happy.
Hi, my name is Maria Norris. My question is to Diyi, and it's actually a three-part question, so bear with me. I'll make it simple. So firstly, you premised your conversation with the introduction of many languages that go beyond the normal languages. So my first question is, do you believe that there's a feminine language and a masculine language? And if so, do you find that there's balance in the large language models? And thirdly, do you believe that there is the possibility of these models becoming what's the word? Basically human-like. There's a word for it, and I just slipped.
Anthropomorphism.
There you go. Those are my questions. Thanks.
Okay, yeah, great question. So actually, I think like the research community actually have studied this type of characteristics related to different gender groups, different like even age groups. There are different variations and patterns in language. So for example, research showed that like if you look at language used to describe female versus male, or language that female use versus male use, there are very different like patterns. I used to have this interactive quiz in my class where if you think about specific word, you can guess who is likely to see that word. So if I have two words, suggestion and proposal, so which social class is more likely to use proposal versus suggestion? Or if you have the word impressive versus amazing, which age group is more likely to use which word versus other? So I can keep asking the question. And there are a lot of gender difference when it comes to that. So this is actually active research called social linguistics in like natural language processing, and a lot of researchers are studying this. And then related to your second question of anthropomorphism, that is, people are building AI to be human-like. If you talk to ChatGPT, their first sentence is, how can I help you today? Well, we usually expect I and how can I help you today from a human. But now AI are built into this kind of very human-like. Is this a good thing or a bad thing? I think the reality is probably more nuanced than that. There are definitely aspects that need us to be concerned. So if you think about a lot of applications such as this kind of character-based role play, where we have news where teenagers fall in love or form relationships with AI because of this kind of very strong anthropomorphism embedded in conversations that lead a human to believe that, hey, I'm actually talking to a human, or I'm talking to the AI. They understand me. They are so cheerful. They are more supportive than my parents. And then, so you can imagine there are a lot of dimensions there. On the other side, I think for a long time, people are thinking about like, okay, machine intelligence, human intelligence, artificial intelligence. Maybe we are building AI to kind of mimic how humans think or behave in certain ways. So that's why we teach them language, even like norms, a lot of other aspects. So I think that there needs to be a really good balance. And this kind of issue of anthropomorphism actually is more and more concerning as large language models are being used in different applications.
Hi, my name is Lilou Sikar-Noël, and I'm a graduate student at San Jose State University. And I was wondering, might be more on the feminist side than the science side, but do you think that science is too gatekeeped by what we call that PhD admission letter these days? Because it feels like there's no opportunity to do research if you don't have that certification, and then it's like a little bit of a loss for people who might not have get into any programs.
I'll take a stab at it. I mean, I do think that there are a lot of barriers to who does science. I think, you know, those barriers are pervasive. You know, the high school education in the United States is very inequitable, and you know, those inequities persist throughout the research enterprise. And you know, there are a lot of challenges to this. I mean, this is something that I have personally worked on, trying to reduce those barriers in many ways for a few decades. We haven't gotten rid of them. I don't think it's only at that stage. It's at many stages, and I think we have to be very conscious of thinking through how do we reduce those barriers at all stages. You know, I personally believe there's a very broad range of people that can usefully contribute to discovery. And so we should think about not only how to reduce the barriers to getting those people into academic spaces, but also how to really engage a broader set of people in our discovery, especially when we have large data sets.
Yeah, I speak to that from, I mean, we did the same in terms of people who want to become a surgeon or want to go to medical school, and there is a a standard process, you know, that you go through in terms of the gatekeeping, if you will. And just as you said that, I think it's an amazing question with respect to this conversation in this meeting. Most of those frameworks and rules were based on traditional data. And now we have an opportunity with different types of data and ways of data discovery to really look at what are the parameters now. If you look, you know, what parameters did we not capture when we developed this process 25 years ago? And so that's the opportunity. I think everyone knows that it's restricted, but it's restricted for a reason based on traditional data that says who's likely to be successful. And that does need to be revisited, and there's opportunities for data discovery in that space.
Can I add to that? When you're thinking about, like, let's take the particular example of PhD admissions, although there's, you know, these instances of selection happen, you know, throughout the lifetime of a researcher. But if you imagine that there are, it's not the case that being admitted to a PhD program is always positive. Right? In fact, being admitted to a PhD program that has requirements that don't meet your background and that you're not prepared for can be a profoundly demoralizing experience. You know, so I've seen people admitted to PhD programs that I was part of where we weren't prepared to support them. They didn't have enough mathematical background to be able to handle the classes that we had, and we didn't have sort of classes to sort of get them ready for the level to bridge, yes, to our classes. And admitting them was, I think, profoundly demoralizing and bad for their careers. So in that context, you can think about admissions or any of these as a prediction problem. Right? And here we are, you know, data-driven predictions, right? And, you know, the programs that I'm part of are very, we like thinking about data, we like being data-driven, but we do not have enough data, right? If you want to say, you know, you're going to take all the information that you have about the applicant and you want to predict whether your PhD program will be causally a positive thing in their life and enable them to do better work than they would otherwise, right? We do not have data on that, right? We have only for the people that we admitted. We can see, you know, we have a little bit of data, like maybe did they graduate or did they not, right? Or, you know, if we were more advanced with, you know, NLP tools, perhaps we could look at the quality of their papers, or we could look at, you know, you'd have to pick a criterion. But actually, there's very, very little data, and we have no data at all on the people that we did admit. So actually, this is completely not a data-driven decision, right? And it's driven by sort of traditional factors that we thought were correlated with outcomes, but actually, we have no idea if they're correlated with outcomes. We've never studied that, right? So perhaps it's a place where data scientists can really make an impact, but you know, the first problem is collecting the data, and that's a shockingly hard challenge.
Thank you so much. Those are really excellent points. Any closing thoughts before we close the panel? Okay, perfect. So thank you so much. Thanks to our panelists, everybody.